Understanding system calls is a must. They are essential for mastering how applications interact with the operating system, and system calls are a favorite topic in tech interviews. In this video, we will uncover the role of system calls in powering modern applications, explore their categories, and discuss how user mode interacts with kernel mode to execute these calls seamlessly. So let's get started. In the last video, we discussed about the user mode and the kernel mode. User mode is where regular applications run. It has limited privileges and it cannot directly access the hardware. Kernel mode is reserved for operating system. It has full access to the hardware and system resources. System call acts as a bridge between user mode and kernel mode. Let's define system calls. A system call is a programmed request from a user space application to operating system's kernel to perform a privileged operation. For example, file IO, file read, write operations, process management, creation of new processes, and memory management related stuff, etc. We'll discuss about different categories of system calls in a while. System calls can be broadly divided into 5 categories. Process management, for example, fork, exec, exit. Process management related system calls are used to create and manage processes. File management. File management related system calls like open, read, write, close, they facilitate the file IO operations. Information maintenance related system calls, for example, get PID, uname, and related system calls, they help us in retrieving the system information. Device management related system calls like IOCTL, read, write, these calls allow program to interact with hardware. And communication related system calls like pipe, send, receive help us to handle interprocess communication and network communication. We'll discuss about each of these categories in great detail in our Mastering System Programming video series. So please like and subscribe if you are interested in learning. In the last video, we briefly discussed how system calls work. Application requests a resource via system call, then mode switch happens, mode changes from user space to kernel space. Kernel recognizes the system call, performs the operation, and returns control to the application. An application then resumes execution. But there were many questions left unanswered. How does an application invoke system call? How is a context switch triggered during system call? How does the kernel identify requested system call? What actions does the kernel take to execute a system call? And how does the kernel return the result to the user application? Let's find out answers for these questions. Now let's understand how system calls are handled in user mode. Let's take write system call as an example. Application calls the libc write function. Libc is a standard C library. It provides user space implementation for system calls and other essential functionality. Libc acts as a bridge between applications and kernel, offering convenient wrappers for system calls like write, read, and other system calls. So libc write function invokes a syscall function. Then this syscall function triggers a context switch. Let's understand how syscall functions triggers a context switch and how arguments are passed to kernel. Write functions take 3 arguments. First one is file descriptor, second is the message buffer that we want to write, and the length of the buffer. And when libc calls the system call, it uses 4 arguments. First one is the system call number, and rest all these 3 arguments. Now how these 4 arguments are passed to kernel and how mode switches from user mode to kernel mode, let's understand in detail. In the context of ARM 32-bit processor, function arguments are passed in registers. So first argument is passed in R0 register, second in R1 register, third in R2, and fourth in R3 register of the ARM processor. Now to pass these arguments to kernel, the system call number is placed in R7 register, syscall number, and rest 3 arguments are placed in R0, R1, and R2. But why are we placing these arguments in R7, R0, R1, and R2 registers? We'll understand about this in a while. But for now, let's assume all these arguments are placed in these registers. Now, how mode switch happens? Mode switch happens because of this SWI instruction. SWI instruction causes a mode switch. SWI instruction is a software interrupt instruction. SWI instruction causes a software interrupt and mode changes from user mode to kernel mode. Let's understand why write system call arguments are passed in those specific registers. In case of ARM 32-bit Linux, R7 register is used for system call number. For write system call, R0 register is used to pass the file descriptor. R1 register is used to pass the buffer pointer, and R2 register is used to pass the buffer count. Each system call has a unique system call number, and this specification defines which register should be used to pass arguments. From user mode perspective, to sum up, application calls the libc write function call. Libc write function call invokes the system call. Syscall function is implemented in assembly. System call related arguments are placed in R7, R0, R1 and R2 registers, and SWI instruction causes a mode switch. Now let's understand what happens next in the kernel mode. Once control is transferred to kernel mode, Linux kernel looks up in the system call table. Here is the example of system call table. This table indicates the system call number and which function should be called for each of the system call. For write system call, 4 number is reserved and the associated function to call is syswrite. After looking up in the system call table, kernel maps the system call number to a corresponding function. So in our case, it maps the 4 number to a syswrite function. This is the example implementation of syswrite function. Syswrite function calls the VFS write function internally and writes the data to the disk or corresponding memory. Then how does the control is transferred to user space back after writing data? Kernel restores the user space context. It places the written value in R0 register. And finally, erate instruction is called to transfer the control back to the user space. And then application resumes. Erate instruction causes a mode switch. What is erate instruction? Erate is written from an exception instruction. So from user mode, we call the SWI instruction. It causes the exception and control is transferred to the kernel mode. And in kernel mode, we call erate instruction to transfer control back to the user mode. Similar concept is used in x86 platform. You can explore as an assignment. If you want to see more educational videos like this, don't forget to like and subscribe. In the next video, we will dive into processes and threads, the heart of operating system. Stay tuned for more exciting contents. Thank you.